Lesson 1 of Chapter 10 is on series and sigma notation, day 2. So first of all, I want to talk about the difference between a sequence and a series. So we've been talking about sequences, and you can see that there's a list of numbers like this, which represents a finite sequence. If you look at a list of numbers like this, that would be an infinite sequence. The difference between them, obviously, is the infinite sequence goes on forever. The finite sequence stops. The finite sequence only has 5 terms in this particular case. Then if you look off to the right, you can see this represents a finite series. A series is not a list of numbers separated by a comma, but a list of numbers separated by an operation. And then down below, this would represent a infinite series, which is a list of numbers separated by an operation, and it goes on forever. So here's some more examples. You can see that the first example right here represents an infinite sequence, and this would represent the same set of numbers, but as a series, it would also be infinite. And so if we talk about partial sums, you can see each term. The first term is 1, the second term is 4, the next term is 7, and then 10. You can see the pattern is it's going up by 3. If we find partial sums, you can see that your first partial sum is 1 right here. Your second partial sum, if you add the first 2 terms, is 5 right here. If you add the first 3 terms, it gives you 12. And then if you add the first 4 terms, it gives you 22. So this list right over here represents the sequence of the first 4 partial sums. That's the sum of the first n terms. And so if we go down to the second example down below, you can see that this represents an infinite sequence. You can see that the pattern is that you're multiplying by 1/10 each time to get the next value. This would represent an infinite series, same set of numbers separated by an operation. And if you looked at the sequence of the first 3 partial sums, this represents the sum of the first term, this represents the sum of the first 2 terms, and this represents the sum of the first 3 terms. So that's some terminology that we'll use is talking about partial sums. Now we've been working with formulas. This particular problem, it says determine whether each sequence is convergent or divergent. And they're giving us a formula. This formula is an explicit formula, which means to find the third term, we just put 3 into the formula. This isn't a recursive formula. So let's find the first couple of terms. Let's find the first term by putting 1 in for n, and that would give us 9. Let's find the second term by putting 2 in for n, and that would give us 6. Let's find the third term by putting 3 in for n, that gives us 3. You can see that the pattern is it's going down by 3 each time. And so what's going to happen with these numbers as we continue to find them is that they're just going to continue to get smaller and smaller. If we were to make a graph of this, it would look something like this. You can see that our first term is 9, and then our second term is 6, and then it keeps going down, and it's going to continue to go down forever. So this is not converging in on a value. This is going to continue to decrease without bound. And so this problem is divergent. Next example, same directions. Determine whether each sequence is convergent or divergent. And this formula is a recursive formula. So it's very, very different. You can see that it gives us the first term is 36. And then this formula right here tells us how to find the next term. Okay? So it's saying to find the second term, take negative 1/2 times the previous term. Again, this right here, this a sub n minus 1, that's representing the term before the nth term. Well, we're trying to find the second term, so we need to use the first term to find the second term. So negative 1/2 times 36 would give us, negative 18. Now to find the third term, we'll have to take negative 1/2 times the second term, which is negative 18. That would give us 9. Well, you can see that the pattern is you're just taking the previous term and multiplying by negative 1/2. And so this pattern would continue. And if we were to make a graph of these numbers, you can see that these data points would alternate from the negative side to the positive side to the negative side to the positive side. And you can see that this is converging in. Now you can see, if we go back and forth, you can see that these values are getting closer and closer to 0. Therefore, this is convergent, and it's converging in on 0. All these values that we're coming up with on the left are getting closer and closer to 0. Here's another example. The same directions determine whether each sequence is convergent or divergent. This formula is an explicit formula. How do I know that it's an explicit formula? Because I don't see any of this. I don't see any a sub n minus 1. That indicates to me that you have to use the previous term to find the next. So to find our first term, we're just going to put 1 in for n. That's going to give us negative 1 times 1 in the numerator. And it's going to give us 5 on the bottom. So that'll give us negative 1/5. If we find our second term, we're putting 2 in for n. That's going to give us 1 times 2 on the numerator, and then 9 on the denominator, which would be 2/9. And if we find the third term, putting 3 in for n, that's going to give us a negative 1 times 3 on the numerator, and a 13 on the denominator, so that's negative 3/13. And so as I continue to find these values, if we were to look at the graph of these, you could see that they're alternating positive and negative. The positive values are getting closer and closer and closer to 1/4. The negative values are getting closer and closer and closer to negative 1/4. And so since these values are not converging in on one particular value, they're converging in on 2 different values, we say that this is divergent. Next, example 5 says to find the fourth partial sum given a formula. Again, looking at this formula, hopefully you can tell that this is an explicit formula, not a recursive. So let's find our first 4 terms, and then let's find the sum of the first 4 terms, because that's what they're asking for with the fourth partial sum. The first term would be found by putting 1 in for n, and that would give us 1. Second term is found by putting 2 in for n, and that would give us 7. Third term is found by putting 3 in for n, and that would give us negative 5. And then the fourth term is found by putting 4 in for n, and that would give us 19. And so your partial sums would be the sum of your first 4 terms. So S sub 4, the fourth partial sum, would represent 1 plus 7 plus a negative 5 plus 19. And so our fourth partial sum would be 22. Example 5 is similar. This time it asks us for the third partial sum because they're asking for that. This formula right here is an explicit formula. So let's find our first 3 terms. We get 4/10, we get 4/100, and we get 4/1000. This is the same thing as 0.004. This is the same thing as 0.04, and this is the same thing as 0.4. So your third partial sum would be 0.4 plus 0.04 plus 0.004, and that would obviously give us 0.444. Hey, the other day I happened to be looking at my math book, and I happened to notice how sad it is. And I was just like, man, that's weird. Why is my math book so sad? And then it dawned on me when Mr. Vogley came in, and he also noticed the same thing. He says, well, that math book, it's just got so many problems. That's why it's so sad. Last thing I want to talk about is sigma notation. So sigma notation looks like this. there's a Greek symbol sigma that we use to represent the summation of terms. Okay, and it looks really complex, but it's not very difficult. Here's an example. This is going to say find the sum, and this is sigma notation. And so you can see there's an index on the bottom, and then there's a limit to your summation on the top, and then there's a formula right here. So what you're going to do is start with the index, the 1. You're going to put 1 into that formula, and that would give you 4 times 1 minus 3 is 1. Then you're going to add the next term and find the next term by putting the next integer. So now we're going to put 2 into the formula, and that would give us 5. And we're going to keep going until we get to the limit, which you can see is right here is 5. So let's see, we're putting in 3, so that's going to give us 9. Hopefully you can see that the pattern is that it's going up by 4 each time. And we're going to stop right here, because if we put in a 1, we get 1. We put in a 2, we get 5. Put in a 3, we get 9. Put in a 4, we get 13. Put in a 5, we get 17, and then we stop. So now if we add up all these numbers, we're going to get, what is that, 15, 28, 38, 45. So there's the sum of that sigma notation. Here's another example. This time you can see that our index starts with a 3. So our first term is found by putting 3 in. So that'll give us 18 minus 3, which is 15 over 2. Now we got to put in a 4. That'll give us 24 minus 3 is 21 over 2. Now we got to put in a 5. That'll give us 27 over 2. Now we got to put in a 6. That'll give us 33 over 2. Now we got to put in a 7, which will give us 39 over 2. Then we stop because we've reached the limit of our summation there. And so hopefully you can see the pattern is the numerator is going up by 6 each time. And so now if we add all these together, we're going to get, let's see here, we got 15 and 21, it gives us 36. 36 and 27 gives us 64. 64 and 33 gives us 97. And then 97 and 39 gives us 136. And then if you take 136 and divide by 2, that would give you, what, 68? So that would be the sum of those terms. One more example. Now this one, you can see that it starts with an index of a 1, and it goes to infinity. So that means it's never going to stop. So we'll start off by putting 1 in for n. That gives us 7/10. And I'm going to write that as a decimal. Now if we put in 2, we're going to get 7/100, which is 0.07. And then if we put in 3 for n, we're going to get 7/1000. And this is going to go on forever. So obviously you can tell that if you add up all these terms, even though it goes on forever, you're going to get 0.7 repeating. So that's an introduction to sigma notation, and also partial sums, and series being convergent or divergent.